right, good morning. How you guys doing? How did it go with the MATLAB assignment? Is that all right? Got the math figured out now that we got to the fractions, and almost a matter of just putting those calculations into place, right? And the question is how. Yeah. Okay. How, everybody else kind of agree coding was a little difficult, but you made it. They make plots. I haven't checked them yet. But feeling all right about that? I mean, you could put it all in one plot. That'd be fine. Or you could, maybe I asked for two. If I asked for log versus the fraction, like LogC versus the fraction maybe, or something. Yeah, I guess you'd have to assume some concentration to do that. So probably one, but there's ways you could have added more. Everybody do one plot or two. Okay, well, good. I'm looking forward to taking a look there. Okay, so today we're going to wrap up this discussion of how do we find a particular H plus concentration given some solution, and then move into the next chapter, chapter 6, where we are working on those plots and understanding kind of how to use them, how to draw them, and understand them. That's going to lead us into the importance of titration and why that makes sense in this graphical sense of dealing with these kind of plots. And we'll get pretty far along that, and then next lecture we'll dive into the titration, I think, is about the timing of it. Okay, so last couple times we talked about taking some solution of acid, HA, for example, or in some cases diprotic acids or other things, and apply some electroneutrality equations, some mass balance equations, putting these equations together in order to say, all right, well, given some condition, we could find H+. Now, today, we're going to just pick up there and say, well, we can also do that with ammonia and ammonium, but it's a bit of an oddball. There's not very many species like this. This may even be the only common one we would ever really encounter, and that is, and it's that way because NH4 plus is the essentially the what would normally be HA. So HA is non-charged, but in that sense, NH4 plus has the charge, and its conjugate base is not charged, whereas HA is not charged and A minus is charged. So it's a little bit inverted compared to what most of these systems will do, and that means the equilibrium constant then looks a bit like this, where we have H plus times NH3 divided by NH4 plus. It's not a huge distinction. All the same principles are going to apply here, but the resulting equations will look a little different given all that. So if we take the alpha fractions, then we could say alpha 0, that's NH4 plus divided by the total nitrogen, total ammonia rather. In a simple case, I guess that's the only nitrogen present. Alpha 1 then would be NH3 plus, so divided by total. And of course, the total is going to be those two combined. We could then do our derivation to say, okay, well, let's find some equation for H plus. And on the way to do that, we would, if we had, let's say, a solution of NH4Cl, so ammonium chloride, then our total constituents would look something like this. We'd have the fraction that is ammonium plus H plus equals the fraction that is plus OH minus, essentially, is what this KW divided by OH. So this would be our condition there, plus Cl minus. So that gives us our electroneutrality equation. We can set that equal to 0. Now, if we had a condition where we made a solution of NH3, then the Cl minus goes to 0 because it's a different case, of course, and everything would follow except that would be 0, and we could solve that way. So that's where we would get this equation where we have NH4 plus OH plus H plus is equal to OH minus. So let's take a look at how that would play out. I'm not going to task you to solve this one directly, but we can simply take a look and see kind of the particular numbers that would come out for this example. So if we take some household ammonia, it's often something like 5% by weight, and we'll say that's 50 grams of ammonia per kilogram of water. Since 1 kilogram, it's mostly, it's approximately 1 liter, we'll say that this is close to 50 grams per liter. So the first question is, what is the formality here? And then the second question, which is kind of the more interesting one, is if the pKa for ammonia is 9.24 at standard conditions, and we're going to ignore activity corrections, and we're going to assume no CO2 is coming in, then the question is, what is the pH at standard temperature and pressure? So we can approach this then. Of course, we can find the formula weight. That's a simple, or formula, using the formula weight, we can find the formula concentration. So then part B, we're going on to apply that pKa and apply that equation we were just taking a look at. So under these conditions, we'll recognize we can make use of the basic solution approximation and that weak base approximation that we talked about last time. That would be the simple way to do it. We could also put it into a solver for the root to 0. So the book's going to take us through that, these approximation equations. And we saw this last time. We have the OH minus can be set equal to the square root of Kb, that's the base constant, times C. And the base constant, we derived also that that's basically the inverse of the pKa, so it's 4.76. And if we were to take a look, we derived it in kind of a fancy manner, but really we could take 14, which is the top of the pH scale, minus 9.26, or 24, excuse me, and get that 4.76, right? So that's, at the end of the day, it's an inversion in that sense. So that's where they're getting Kb at this value. Okay, so solving that, we get a pH of 11.85. All right, so I just kind of wanted to walk through that real quick. Now we have an idea of what pHs are ammonia at home, and we can kind of see, we can do the same process we've been doing on this special case. So the book goes on, or the example goes on to say it's a rather high pH, and this is why it's rather good at cleaning, especially for grease, oils and greases. There's a fancy word that I learned, saponify. So to make fatty molecules into soap, that's the word for it. And basically the high pH can help dissolve that, and you're essentially making more soap from those oily compounds in the process. Okay, now another thing it's noting is that we've got a high activity, and for pHs that are high above the pKa there, almost all of this is going to be in NH3 form, and NH3 is volatile. So whenever we're dealing with ammonia chemistry, whether it's household stuff or it's ammonia stripping for water treatment or something like that, what you'll recognize is basic conditions allow for that, for us to use the volatilization or one way or the other to take ammonia out of the air or to release ammonia into the air that's under basic conditions is where that's possible, because it's NH4 plus, since it's charged, cannot volatilize. Charged species cannot volatilize. They're stuck in solution. Okay. So I think that's about all I wanted to say for that. I guess one other thing to add in here is we can set up a suite of these alpha values if we had a complex situation. So if we had, for example, acetic acid as A, family A for acetic acid, and the acetate ion, family C for the carbonate system, and family N for the ammonia system, then we can set up an electroneutrality equation for all of this and simply label our alpha fractions individually, right? So alpha 0 for the ammonia system, alpha 1 with the carbonate, alpha 2 with the carbonate, alpha 1 with the acetic acid. So we could put all of that into place and make a larger system. And the book goes through another Excel example for that. The cool thing is that we can essentially use the same root approach, because this left-hand side minus right-hand side still works out, and the shape of it, if we were doing it in that approach, will work out nicely for us to make that guess and figure out what is our pH. So we can kind of use all of that same stuff with a more complicated condition, is the point. And if we want to, we can complicate it further and add the activity corrections. Under relatively dilute situations, we don't need to. So we're not going to even touch on that. I'm just letting you know that's there, and the book describes that as well. Okay, so that's it for the cases where we were considering a particular system and trying to find that pH. Now we're going to take a look at more so we have a system and we're going to move across pHs within that system. That's kind of the theme of chapter 6 here, and it's introducing this role of a strong base, specifically heading towards, okay, what's going to happen when we titrate? If you remember from general chemistry, if you did any titration experiments in the lab, typically you're adding NaOH or KOH, so some strong base, and watching for when you've added enough for something to happen. And at that moment, you know then something about how much concentration to know how much base you had to add. As we'll see today, that's telling you information about how much of the acid is there to reach that equivalence point. I have to apologize, I've used the word equivalence point incorrectly a few times earlier in this class, so we're going to clarify that today as well. Okay, so moving within a system, the example here is if we have acetic acid or some other HA, and we have a known concentration, we might ask how much base, how much NaOH would be required to achieve some different pH, and then we can say, well, what is the speciation there? So we can kind of do both of those things at the same time. And it even goes on to say, well, in the next few chapters, starting here, we could look at, can we answer the question in a more complex system? If we spill some hydrochloric acid in a stream, will that result in a low enough pH to kill the fish? Right, so that's kind of a overall application type of goal that we're heading towards with this type of discussion. Okay, so as we're going to build a plot, we've already actually seen this quite a bit, and in some ways I feel like I should have just started the whole class with these plots. So I've got a little bit of mixed feelings with how the book's going about it, but here we are. So we've talked already about taking a monoprotic acid, some generic HA. It's going to be in equilibrium with A minus, H plus, or we could look at ammonia, slightly different. And we could get these alpha fractions. Alpha 0, that's the portion that is still protonated, so HA with respect to the total. And alpha 1, of course, is lost 1 proton, and that species with respect to the total. We can put this in log form and say log of HA is equal to log of alpha 0 plus log of the total. Now that's essentially taking log of both sides and then making use of the log relationships to get there. I'll elaborate here. So we can say, if we started with this alpha 0, I'm going to write it like this. Alpha 0 is equal to HA divided by total. Then log of alpha 0, if we're taking the log of both sides, would be like this. And if we remember, when we have a log of something divided like that, that would be the same thing as writing log of HA minus the log of AT there. So that's where we're getting this relationship, because then we can add log, add this to both sides, and the book swaps sides also. So we could say, I'll just write it out like this: log of alpha 0 plus log of the total is equal to log of HA. Okay, so that's how they're deriving these two expressions from there. Okay, with that, we can then kind of take a look at how, if we're solving for one piece or the other, it's just a convenient expression we can plug into our plotting. So we'll assume activities 1 like we have been. And we also derived previously these alpha fractions in terms of the equilibrium constants. So we could say that given the fact that we found these equations previously, we can then multiply the numerator and the denominator by h plus, and it becomes this term here. H plus divided by h plus plus ka is equal to our alpha 0. You remember deriving that stuff? Okay. So we get that for alpha 0 and alpha 1, and then we can take a look at, in a moment, what happens when we have a very small h plus compared to ka, or vice versa. And that'll kind of tell us what the plot is going to look like, or what the shape is going to look like as we're in one condition or the other. When we go to plot these equations, plotting the log of alpha 1 or 0 versus pH, we can use these relationships, right, in either case, in either form. So as we do that, what we'll find, as we've already seen, is at very acidic conditions, low pH, the alpha 0 is close to 1, so the log is close to 0, log of alpha. So when you ask the question, 10 to the power of what equals 1, the answer becomes 0, right? So that's why we're saying, so I'll say log base 10, well, how should I write this? If we're wondering how to get there, ten to the power of 0 equals 1, right? So that would be the right. All right. So all that just to say is, like, we can get a schematic of, like, when are we almost all in the alpha 0 form versus alpha 1. The other things we can look at here is, first of all, the pKa, and this is where I had been, and I think I even mistakenly put it here. So pardon this, and I will correct this later. Well, we're not looking at the equivalence point on this plot. What we might consider as the equivalence point Like it makes sense if we're thinking, okay, the two fractions are equivalent. Yeah, that's what I was thinking of. That's the wrong terminology. So we have a slide to correct that later. We do find the pKa point. That is the point where the two species are equal. So in that sense, equivalence, but don't call it equivalence point because that's not the terminology here. So we do recognize that at the pK, if the pH is at pKa, then these guys, HA and A minus, are equal. So the fractions then would both be 0.5 at this case. So alpha 0 equals alpha 1 equals 50% of the solution. So we know that, and oops, I'm trying to erase that. So we know that, and we can take a look and describe different points here. And between the moments where we have that flat asymptotic relationship and the other one has that flat relationship, the region between those takes up about 1 pH, so 1 log total, before we're really pretty much all of it's in one form or the other. So in that space between, we would call that transition region. That's a case or a situation where we might recognize, okay, we can't really assume to know exactly what the differences are here within that range. If we go further, maybe we can make some assumption that, yeah, most of it's not this, right? So if we take chlorine as an example, the pKa is about 7.5. So between pH 7 and 8, that's our transition region then. And so within that range, we might have to do some calculations. But if we go to, let's say, pH 6.5, then we're getting to the point where we're pretty close to most of it's going to be in a HOCl form. If we get up to above 8, maybe 8.5, most of it's going to be in the OCl minus form. So we're starting to get to a point where we could assume that 95% or more is one or the other. Okay, so that's kind of the scheme here. A couple other things that we can see if we look closely, and I think we'll elaborate a little bit on this. The drop from 0 to this point where they meet is a known quantity. We can say that's, I think it's 0.3 logs below the top, and that would be coming out from the log of 1/2. We could figure that out. Okay, so a few, and here's the description here. So a few important characteristics in this nice table here. So the curves are going to cross when pKa is equal to pH, or the vice versa. They're each half. Then we can say the log of 1/2 is equal to the minus log of 2, which that's just the log rules. We could figure that, you could see that, which is going to be equal to negative 0.301. And that's the drop that I was talking about. This little graph is a little too small, but if we look at the two graphs doing this, and we wanted to know this drop here, that is 0.301 logs. It's not drawn particularly well, but that's the value. Okay, so then we know that at anytime we have one of these Ka values, we know that the xy coordinates here would be pKa, comma, minus 0.301 on this log scale. So that can be convenient. And if we have a known concentration and we just then want to know what is the result, we could put that in and figure that out. Of course, if we have a known concentration, we know it's about half, so we could also just divide by 2. Okay, so otherwise, the other things I've described is pretty much described here, encapsulated, probably written a little more clearly. And the other thing is the slopes here on the log-log plot are going to be approximately 1, at least in the linear range. So the slope should be 1 here and -1 here. Okay. So let's look at the simplifying scenarios when we are a little bit further away from that transition zone. So in this region or in this region. And this is kind of a bit of a closer look at what makes these acid-base approximations. So if we have a condition where the pH is much larger than pKa, that's over here, right? And this plot that I'm using on the bottom, that's generic, right? We don't know the pH there. The pH scale is arbitrary. So as long as we are, the current pH is above the pKa, which we could write here, then the following, or we could say describe the following about it. So we will say that when the H plus concentration is less than 1/10 of Ka. That's basically saying we are at least 1 order of magnitude to the right of the Ka. So usually we'll say this as, you know, as written here or as the heading says. But in practical terms, since we're defining that as we have a lot less H plus, therefore a lot less acidity in comparison and by a factor of 10, then we could say this 1 order of magnitude shift to the right. So that's getting us clearly outside of that transition region, essentially. Now, under these conditions, then we can simplify from these alpha equations we had previously, we can simplify to get simpler alpha fractions. And in the case of alpha 0, so recall that we're looking at alpha 0 over here and alpha 1 over here, the fraction that is protonated versus the fraction that is not protonated. Then for alpha 0, we had this equation over on the right, and we're going to say that now it's approximately the H plus divided by Ka. And the reason we're going to say that is because this equation here, we have the H plus on the numerator, and even if it's very small, it's still there. And then on the denominator, the relative importance of the two means that the H plus kind of goes away, leaving us with H plus over Ka. So even though the H plus is still there, if the H plus is 10 to the minus 10 and the Ka is 10 to the minus 7, the difference of having that H plus there is the third decimal place along. So it really doesn't make much of an impact. It still makes an impact on the numerator. It's still important there. But relatively speaking, this, it's not technically 0, but it's approximately 0 for the purposes of our calculation. It's, we'll just say very small. So that then gives us this equation. Now we can do the same thing with the alpha 1, and this is showing us that it's going to end up being approximately Ka over Ka, which is 1. And again, here we see if this, under these conditions, is very small compared to Ka, then we get Ka over Ka. Okay, so that's like the technical way to look at it, how we're deriving it, how we're coming to those conclusions. Now, when we go to calculate the slopes, we can take a look at it as the dy versus dx kind of a look. That's our slope, and in this case, we're stepping along this log of the alpha fraction versus the log of pH. And Under these conditions, our slope of alpha 0 is going to be negative 1, like we said. So this is d log alpha 0. And on the left side, that would be, well, we're still on the right side for this case example, actually. So over here, the slope is approximately 0, right? And all of this is looking at kind of this region. Okay, following all that, that makes sense? So we can do the same type of consideration for the left side of this. Yeah. This one?
I'm a bit confused. So let's say that pH of 3.
Yeah.
So let's say you trace up, should you get an alpha 0 and alpha 1 value, or you get just an alpha 0 value?
You could get both. You say if we trace up from pH 3, right? So we'll run into an alpha 1 value there and an alpha 0 value here.
So we take both, or we just take alpha 1?
What do you mean by we'll take them? Like,
I recall you saying you can use it to describe which species you have in abundance in a system.
Yeah.
So if you have 3, does that mean 3 is acidic, so you have more of, let's say you have more of the H plus there as compared to the other species, let's say HA.
Right.
So I can see log A is equal to 0.
Mm-hmm.
And so does that mean that we don't have any log A over there?
It's approximately 0. So let me show you what this might look like. So at pH 3, alpha 0 is close to, we said it's close to 1. The log of it would be close to 0, right? So I'm gonna switch from using log for a moment so we can maybe use it a little more intuitively. And I'm gonna say, really, it's probably 0.997 or something like that. And we can calculate that exactly if we want to. And that would mean that alpha 1 is approximately 0 in the in the raw form, not log. In the log sense, it would be what, -2.5 or something. And if we calculate it exactly, it might be 0.003. So under those conditions, the log of alpha 0 is almost 0 because it's very close to the alpha 0 value is close to 1. So if we take the log of, let's do that. If we take, can I do log? No. Log of 0.997, that value is 0.0013, -0.1. So it's close to 0 is the point, right? And so if we had a problem that we were not so sure exactly where we're ending up, that approximation is very convenient. And so we say, oh, okay, well, the concentration is approximately the total. That's kind of the point. That's a good question there. Does that clarify it for you? Okay. And of course, every pH we step away from the pKa, it's 1 log additional difference there. Okay. So given that, let's put that into practice. So here's another example for us. We're going to estimate the values, the alpha values, based on pH and pKa. So we have a standard condition here and two scenarios to look at. The first is a solution containing some ammonia that has a pH of 8.1 And don't do any calculations, like any complicated calculations. You could do like a addition or subtraction, I guess. Without anything more, estimate the value for alpha 0 and alpha 1. If the pKa for scenario A is 9.24. So maybe it might help to draw up here. So I'll do it in red for the ammonia. Let's do this. So I suggest you draw a little chart like this or similar for yourself as well. You know what I ought to do? All right, keep thinking about that and working on that for a moment. I'm just going to duplicate this chart so we have two spots to work with. wanted to make sure I was being a little more clear, so I added the second figure here. We could take the pH markations down here at the bottom. Now, we have this very generic graph. And so normally we'd put like that middle one as pH 7 and continue on from there. And then put our graphs where they need to be, or put our lines where they need to be. In this case, I'm just taking this generic one and saying, okay, I'm going to shift this x-axis as I need to match that middle section being the pKa. And so what I did was at the bottom I labeled, okay, that's the pKa, 4.76. One notch over would be 5.76, and then 6.76, and so on. And I was trying to write too small and it didn't work very well. But for both of them, we could do that and shift either way, and then visualize pretty easily, oh, okay, here's a little over for the ammonia case. From 9.24, we could go down one tick. That's 8.24. So just a little past that is the spot where we could draw our line and say, okay, here's our values. So I kind of drew that up for both of them. And I think the book's going to give us perhaps even a simpler way to go about it. But even though they told us not to do calculations, they did a couple. So they say for part A, 9.24 minus 8.1 is 1.14. So that's just over 1 log change, like I was talking about. So the alpha 1 should be approximately 10 to the minus 1.4. So that's going to be coming from, and the alpha 0 is going to be 1 minus that. So we could always relate one to the other. We can always say alpha 1 is going to be 1 minus alpha 0, right, and vice versa. So what they're doing here is saying if the alpha 1 fraction is 10 to the minus 1.14, then the alpha 0 is going to be 1 minus that. So I guess this is their lower level of calculations to describe that. And yeah, that's kind of based on those principles we had been taking a look at so far. All right. So when we go to plot a log concentration versus pH, it's almost the same thing, right? In fact, we could take those alpha fractions and multiply it by our total concentration and get the exact same plot. However, we can do a few things that that are perhaps a little more interesting, and we can understand something a little more about how much acid or how much base or whatever we're dealing with if we put it on a concentration scale. So we're going to do log concentration here. We have another example that we can follow, and the book gives us this nice box to say, okay, here are the instructions on how to draw up a log concentration plot. If we follow these steps for this HA/A- system, we'll get a nice plot. So it's asking us to essentially draw up this system for an HA with a total acid concentration of 10 to the minus 4 molar and a pKa of 6. So let's take a few minutes. The book also has the completed version of this we'll take a look at. But let's step through this together. I'll give you a couple minutes. I'll read through it and then give you a couple minutes to start sketching, and then we'll go one by one to see to put it together. Okay, so on a grid with log H plus and log OH minus plotted, so that's already there, and we know that's always going to be the case. It's always going to look like that in terms of starting at minus 14 for the log of OH at pH 0. There's almost none of it, all the way up to 1 at pH 14, and the inverse for H plus. So starting with that, we can locate and mark the XY point given the pKa and the log of 8 total. In fact, let's just go ahead and do that now. So mentally or graphically on your paper, plot that point. So we know it's going to be on the pH6 value, right? It's going to be here. Question becomes, how far down is it for these? Well, we can take alpha 0 at this point is equal to alpha 1 equal to 0.5. And then we also know that we can write the, let's say, HA concentration is equal to alpha 0 times the total concentration. Right, so if we know the total, we could take half that. We could also do the log version of that. And if we take the log of that, would be saying log of alpha 0 plus log of A total. We're given the A total in 10 to the minus 4, so we already know that's going to be minus 4 there. The log of 0.5, I think that was the 0.3 value that we had, right? The negative 0.301 plus negative 4 should put us at negative 4.3. So that should be our spot. Make sense? Okay, if we want to, then step 2 says we can lightly mark the transition zone, which should kind of be, oh, come on. Kind of be 1 log range here. Maybe I can do light sketches. No, probably not. We'll just make a little note here. So in that range will be the transition. Step 3 says draw 2 horizontal lines at the value of log A total. And we'll do that for HA from the low pH almost up to the pKa minus 1. So almost to the end of that transition zone. So the total value that's 10 to the minus 4. So we're going to draw here almost to that minus 1, and it's going to go on and tell us to do the same thing from almost 1 above it across. Something like that. Okay, next up is draw for HA, draw a line with a slope of -1 from high pH to lower pH that passes through the point we marked in step 2. Let's see. Okay, so if this line here is our transition zone, we're saying slope -1 from high pH to lower pH that passes through, we didn't mark a point in step 2. Okay, so I think what we're saying is essentially draw a dashed line like this that would intercept with that. With a slope of 1. Okay, at the point where they cross, of course, let's see. Maybe I got ahead of myself in step 1. Yeah, I'm sorry. I got ahead of myself in step 1, drawing it lower. Okay. Here's the deal. In step 1, I should have just drawn the pKa point at the A total. Is what they wanted. Okay, whatever. Which was right here. And then later we drop it to the 0.3, and we're supposed to draw these dashed lines through the top one. And then once we get that point, then we actually draw them through that point, I think is the deal. Yeah. So the point was to try to do this, something like that, through okay, so I didn't do that particularly well, but you can kind of see the way we can approach that. Say, all right, here's the total, here's the, if at that midpoint, they're each going to be half, and we can plot that directly on a log plot by subtracting 0.3. So it's not a huge difference visibly on a log plot, and we can sketch out all these other pieces. Okay. If we did it better, this is what that would look like. Okay, so we see that we have the H plus and the OH minus. These are those lines there. We have this dot here marking pKa and log total. But of course, where they actually meet is going to be lower than that. So they marked out this region here where they did dashed lines, and it gets a little convoluted. But essentially, they're going to cross at that. They're going to actually meet at that 0.3 under the total and continue on from there. Okay, this is for pKa6 and the total concentration of 10 to the minus 4. So as we think about this, if we change the total concentration, we can clearly see that that's going to increase or decrease it on this plot, up or down. And the interesting thing here, and this is what will bring us towards the equivalent point, is, well, how does that relate to how much H plus there is in solution? Because at some point we're going to get to the point where the H plus is more dominant than the amount of acid that we have or that we have added. Okay, so that brings us to this equivalent point thing. So again, I apologize for the confusion. Even I need to edit slide 2. the equivalence point is different than that point, the pKa point. Okay, it's a different concept altogether. This is where a solution for HA, it's a solution of HA. We'll call it at the equivalence point when we've added a strong acid, like HCl, to a solution of NaA. So NaA, this is just Na plus, which does nothing, and A minus. So if we start with that, we have a bunch of A minus, and then we add enough acid to get to where we are at a particular point. That's the equivalent point. So there's two examples here that are both at the equivalent point. And by the way, that's equivalent amount of acid that would get us the same concentration of A minus that we have in solution. So try to make that a little more clear. So if we added enough NaA to get a 1 mole per liter solution, but we added it all as NaA, then we add an equivalent amount of HCl to achieve the current amount of HA there. Okay, so let's take a look at these examples. So we've reached the equivalent point for both of these scenarios. We have the HA equivalent point for the acetic acid system. 1 is 10 to the minus 3 formula weight of acetic acid in 1 liter of water, and 2, the formula weight, 10 to the minus 3 formula weight of it, sodium acetate plus that same molar amount, so the same formula weight, 10 to the minus 3 of HCl in 1 liter of water. So if we start with just purely acetic acid, that will get us to the same equivalent point as if we started with sodium acetate and then added that same molar ratio of HCl. That's, even in my own mind, it just doesn't feel very clear at this moment, but when we look at it graphically, it will become a little more clear. So I'm going to move on for just a moment. Couple quick reminders here that if we do the electroneutrality and the proton balance for these equations, electroneutrality says H plus is equal to OH minus plus A minus, and we can use the acidic solution approximation if we have a solution like that, so that approximately the amount of H plus we're adding is equal to the A minus. This is actually kind of why this equivalence point makes some sense. Okay, so if we find the process of finding a pH for a solution, I'll just read this. So this scenario indicates that process of finding the pH of a solution of HA might proceed by preparing the plot graphically and locating where the log of H plus crosses the log of A minus line. So when we plot this with that H plus and the OH minus, we can take a look at that. So what we're talking about here is finding when this line meets this line, right? So right here, that's the equivalence point. Because what we're dealing with is at some amount of A minus in solution, if we add enough pH to get there, that's getting us that condition where H plus is equal to A minus. Right? And I have it written up there actually. So when we land there, that means we found the equivalence point. And in this case, that's pH of 4, I think. Okay, so we can take a look at that for different systems. So in this case, this chart A here, that's a fairly similar case to what we were looking at earlier, except we have 10 to the minus 3 concentration, and the pKa is 5. panel B, we're going to take the same acid, so the same pKa of 5, and this time we're going to put it at 10 to the minus 4 instead of 10 to the minus 3. And now we take a look at that equivalent point. It's right here, and we notice that's actually quite close to the pKa. What that can tell us is that under one condition, condition A with enough acid, we are kind of past that transition point or passing that transition point, and we can then use the that acidic solution approximation. Here, where we are closer to, or we are solidly within the transition point, that means we don't have a big difference between HA minus and H plus. So the acidic solution approximation, this basically assumes that one form is not really there to much extent, right? So we would assume A minus is negligible for, I think it's the ENE portion of that. That's how we get to here from the ENE and the proton balance, right? That's the condition there. Okay, so with that in mind, if we're taking a look at panel B, we see that we're not really in a good spot where we can make that assumption right there, because we do have certainly HA and A minus in solution. They're rather close to the same amounts too. Okay, if we take then that same dilution of acid, 10 to the minus 4, but we're using a different pKa, so pKa is 6 in this case. At this point, our equivalent point is here, and it's looking a bit better. So if we change the concentration or we change the pKa, that's going to change whether or not the acidic solution approximation is reasonable, and also the weak acid approximation. Okay, so that equivalence point is then telling us something pretty useful about all that. Does that make sense? Okay, we can then also think about kind of the inverse and the NAA equivalent point. So it's kind of like the basic version of the acidic equivalence point. So in this case, the equivalent point is reached when we add enough NaOH or some other strong base to meet the conditions where if we started with just HA, now we have the same amount of A minus in solution. Because again, in this case, we have NaA going to A minus, and well, in this case, probably not a equilibrium. And Na plus, which is going to be just a spectator ion, doesn't do anything. Okay, so just a quick reminder, we can go through the same electroneutrality assumptions and things like that to find our basic solution approximation. Again, that essentially we're saying that there's not very much HA and, not very much H plus in that condition, so it becomes kind of negligible, and our system, ultimately we can relate HA is approximately equal to the amount of OH minus there is. Okay, that kind of leads us towards the idea of titrating a system where we're adding some amount of NaOH until we reach a point where the chemistry changes because we've hit that equivalence point. So I'm going to pick up there, elaborate a little further on chapter 6. We're pretty much done with it already though, and next time we'll talk about titrations, is my plan. All right.